Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 4 on parallelograms, Day 2. So it's really important that you've actually seen or worked through Day 1 of our parallelogram work, because in that day we looked at all sorts of different things like the definition of a parallelogram and properties of parallelograms and things like that. And we will start today with a little bit of review on that, but then we will quickly move forward with more work on parallelograms. So let's get to it and start with a little bit of review. Parallelogram properties. We have now explored and proved various properties of parallelograms. In this lesson, we will explore various methods for proving a figure is a parallelogram, right? So in our previous lesson, we looked at, look, if this is a parallelogram, what can we say about its properties? All right, or what can we prove about its properties? Today, after exercise 1, we're going to be primarily concentrating on how can we prove that a quadrilateral is a parallelogram. So let's first review the properties of parallelograms that we proved in the last lesson. Exercise number 1. In the image below, ABCD is a parallelogram whose diagonals intersect at point M. Below, write the definition of a parallelogram along with 4 major properties. Now, it's really kind of critical because there is the definition of a figure, like literally how we define what makes something a parallelogram. And then there are the properties, additional things that are true about the figure based on the definition. So, the definition of a parallelogram, make no doubt about it, right, is that it is a quadrilateral with 2 pairs of parallel sides. Now you might say, oh, but it's a quadrilateral with 2 pairs of parallel sides that are the same length and da-da-da-da-da-da-da. No. Everything about a parallelogram after this we proved, okay? This is what makes a parallelogram a parallelogram. It's a quadrilateral with 2 pairs of parallel sides. Now, what are the major properties of parallelograms that we proved in the last lesson? Well, I'd like you to pause the video right now and see if you can remember the 4 major things that we proved about parallelograms from the last lesson. Pause the video now and take a moment to write down as many of these as you can remember. Well, probably the first couple things that we did, well, not probably, but definitely the first 2 things that we did was we proved some things about the angles of parallelograms. One thing that we proved were that adjacent angles, all right, so angles that sit next to each other, adjacent angles are supplementary. They add up to 180 degrees. We then use that fact to prove that opposite angles are congruent. And if you said opposite angles are equal, I'm comfortable with that too, right? But these were the 2 things that we proved about the angles. So angle BAD is supplementary to angle ADC, and angle ADC is congruent to angle ABC, right? Just as examples of these 2. Then we proved some things about lengths, and one of the most important properties that's pretty obvious when you look at a parallelogram is that opposite sides are congruent. Or again, if you said opposite sides are equal, I'm very comfortable with that. So opposite sides are congruent. And finally, one of the less obvious ones, but very important for our purposes, is that the 2 diagonals bisect each other. All right, let me give myself a little more room here. So the diagonals bisect each other. Gonna drive me nuts, the magic red pen. All right. So what I'd like you to do is pause the video for a moment, right, and write down any of these that you might need to. All right, let's move on. Now, the rest of the lesson is going to be devoted to proving that figures are parallelograms. All right, proving that they're parallelograms. So let's look at literally the most basic parallelogram proof. In other words, the most basic way of proving that a figure is a parallelogram. Exercise number 2. In the diagram shown, angle 1 is congruent to angle 3, and angle 2 is congruent to angle 4. Explain why EFGH must be a parallelogram. All right, well, let's just mark up the givens that we know. All right, so I know that angle 1 is congruent to angle 3, and I know angle 4 is congruent to angle 2. Now, what I'd like you to do just for a moment is I'd like you to pause the video and I'd like you to think about how this information allows us to conclude that that quadrilateral EFGH is in fact a parallelogram. Pause the video now and just think about this, then we'll talk about it and get it down. All right, well, way back in Unit 3, when we did a lot of work with Euclidean geometry, we spent a few lessons talking about parallel lines, parallel line properties, and most importantly, how to prove that two lines were parallel. And one of the ways that we saw that we could prove that two lines were parallel was if two lines created alternate interior angle pairs that were congruent, then those sides or those lines or segments would have to be parallel. Well, 1 and 3 are alternate interior angles. And because 1 and 3 are congruent to each other, that means that EF must be parallel to HG. All right? But likewise, angle 4 and angle 2 are alternate interior angles created by EH and FG. And because we know that those two are congruent, we know that EH must be parallel to FG. And now we have a figure that literally fits the definition of a parallelogram. It is a quadrilateral with two pairs of parallel sides. So let's get that reasoning down, right? Because angle 1 is congruent to angle 3, EF is parallel to HG because a pair of alternate interior angles are congruent. Similarly, since angle 2 is congruent to angle 4, EH must be parallel to FG. So EFGH is a parallelogram because it has two pairs of parallel sides. Every time I think I know when the red pen's going to come out, it doesn't do it, and every time I don't, it does. So that's it, right? And that is literally the most basic way of proving that a figure is parallelogram, is by literally proving that it fits what's known as the definition of a parallelogram. Okay? That's it. So now, let's see how else we can prove that something is a parallelogram. All right. We're going to now start to talk about what in math are known as sufficient conditions. Now, the word sufficient basically means enough, okay? Enough. So there are certain conditions that are enough or sufficient for us to say that a figure is a parallelogram. This is very similar to how we had things like the side, 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 or angle, side, angle, or side, angle, side, sufficient conditions in order to prove that two triangles were congruent. Now, we will prove each set of conditions and then can use them in further proof. Okay? So that's very important. Once we prove a particular set of conditions is sufficient to know that a figure is a parallelogram, we can then go on and use that later on to prove other sets of sufficient conditions, which is kind of cool. But that is sort of the bigger picture of math and geometry in general, which is that once we prove something, we can use it to prove something else and use it to prove something else, etc. So let's look at the first set of sufficient conditions for parallelograms. Sufficient condition set number 1 for parallelograms. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. All right, now make sure that you understand this, right? The definition of a parallelogram is that it is a quadrilateral, right, with 2 pairs of parallel sides. But now I'm claiming that if you have a quadrilateral that has both pairs of opposite sides being congruent, being the same length, then you can also say that it's a parallelogram. Now that might seem obvious, but again, we should prove it. So let's take a look at exercise number 3, which is one of those situations, random blue line, one of those situations where we're just going to fill in the reasons on this proof. But let's take a look at it. Exercise number 3. Given that MN is congruent to PQ and NP is congruent to QM, prove that MNPQ is a parallelogram. Fill in the missing reasons for this proof. All right. Well, what I'd like you to do is pause the video now and see if you can fill in all the missing reasons that go from that step 1, where we've got our givens, all the way to that final step where we are able to conclude that MNPQ must be a parallelogram. Pause the video now and see if you can fill in these reasons. All right, well, let's talk about the flow of the proof as we fill in the reasons. First, I just want to mark up those givens, right? MN is congruent to PQ, NP is congruent to MQ. All right, and those are given, and we've already got that put in. Now, the second line of our proof says that NQ is congruent to NQ. I'm going to mark that up with 3 dashes, and we always know that when we say that anything is congruent to itself, that is known as the reflexive property. Now, we can actually claim that triangle MNQ is congruent to triangle PNQ, and that is by the side-side-side congruence theorem. You know, it's the first congruence theorem that we ever saw, and yet we don't tend to use it that much because it doesn't come up a lot. But here it is, right? Here it is. I can now say that that triangle and that triangle are congruent. Now, once I say that those 2 triangles are congruent, I can now say that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. This should start to look a little bit familiar to our last problem, right? Why can I say that? Well, that's CPCTC, right? Those pairs of angles are corresponding parts of congruent triangles that we just proved congruent in step 3. Now, again, from here on down, it's really the proof that we had in exercise number 2. We can now say that MN is parallel to PQ and NP is parallel to QM, and some reasoning like this. If alternate interior angles are congruent, then the lines are parallel, or if alternate interior angles created by 2 lines are congruent, then the lines are parallel, something to that effect. And finally, right, MNPQ is a parallelogram. We can literally just write down that is the definition of a parallelogram. Right? And that is the definition of a parallelogram, right? That it's got 2 pairs of opposite sides that are parallel. Now, this is fantastic because now, even though the definition of a parallelogram is that 2 pairs of sides are parallel, we can now say that if we have 2 pairs of opposite sides that are congruent, it's also a parallelogram. All right? Pause the video now and write down any of these reasons that you might need to. All right, let's move on and continue to look at sufficient conditions. So now let's look at sufficient condition set number 2 for parallelograms. If one pair of opposite sides of a quadrilateral is both parallel and congruent, it is a parallelogram. Now this is kind of cool, and really get this, right? So, our first way of proving parallelograms, a quadrilateral is a parallelogram, is just proving that it fits the definition of a parallelogram, i.e. it's got 2 pairs of parallel sides. Our second condition, right, is that I've got 2 pairs of opposite sides that are congruent. They're the same length. This one, though, this one's a little tricky. This one says if I've got a single pair of sides that's both parallel and the same length, then it has to be a parallelogram. But it's got to be the same pair of sides. So let's prove this sufficient condition set number 2. Exercise number 4. Given QR is congruent to ST and segment QR is parallel to segment ST, prove that QRST is a parallelogram. All right, now for this, we're going to have to draw in an auxiliary line to help us with the proof, all right? So letter A asks us to draw in one of the diagonals of QRST. And it really wouldn't matter which one, but I gotta get triangles involved in this, all right? I'm going to draw in diagonal QS. And again, this is one of the weirdest things for students in geometry, this idea that I can just sort of like randomly draw in a segment on a picture. But remember, I'm drawing this in and it doesn't change anything about the figure whatsoever. It just helps me maybe then prove what I'm trying to prove. All right, now let's take a look at letter B. Mark any angles that you know are congruent based on the fact that QR, segment QR, is parallel to segment ST. Now be careful here, right? We know that QR is parallel to ST. We also know that QR is congruent to ST, but we know absolutely nothing yet about QT and RS, okay? So pause the video now and mark any angles that you know are congruent based on these two segments being parallel to each other. Well, there's actually only one pair of angles, right? It's angle RQS and angle TSQ. Those two angles must be congruent based on the fact that those two segments are parallel to each other. Now let's take a look at letter C. Write a strategy for how to prove the two triangles you created in A are congruent. All right, so in other words, like a lot of the proof in terms of quadrilaterals and parallelograms rests on us proving that two triangles are congruent, which seems a little weird, but you've seen it enough now that hopefully you're starting to be comfortable with it. So think about this for a moment. Pause the video now. How would I go about showing that these two triangles are congruent to each other? All right, well, I know that this side is congruent to this side because it's given. I know that this angle is congruent to this angle because they're alternate interior angles created by these two parallel line segments. And finally, I know, of course, that QS is congruent to itself because of the reflexive property. So I'm going to be able to prove that triangle RQS is congruent to triangle TSQ by the side angle side theorem, right? So we can use side angle side because QR is congruent to TS, angle, maybe put a comma, angle RQS is congruent to angle TSQ, and angle QS is congruent to itself. All right, you've seen that come up time and time again, that reflexive property thing. All right, so now let's take a look at letter D. Use C along with the first sufficient condition to formally prove that QRST is a parallelogram. All right, so this is really cool. I'm claiming that we can use the fact that we can prove these two triangles are congruent, and we'll have to do that within the proof, along with what we saw in the first sufficient condition, which was, right, if I have a quadrilateral with both pairs of opposite sides being congruent, that it must be a parallelogram, I can put those two together to prove sufficient condition set number 2, i.e. that if I've got one set of sides that is both parallel and congruent, that also tells me that I have a parallelogram. Pause the video now and see if you can get that proof down. Keep in mind that the first thing that you're really going to be doing is proving that this triangle and this triangle are congruent to one another. All right, let's take a look. So let's start with those givens, right? QR is congruent to ST and QR is parallel to ST. Simple enough, given, right? Now we have angle SQR is congruent to angle QST. That's our alternate interior angles created by parallel lines are congruent. Simple enough. QS is congruent to QS by the reflexive property. All right, this is all just what we kind of outlined in letter B. And triangle QST is congruent to triangle SQR by the side angle side congruence theorem. Awesome, right? But now, where do we go from there? Well, keep in mind, we already knew that QR and ST were congruent to each other. But now that we know that these two triangles are congruent to each other, we can also say that QT is congruent to SR. And I'm going to state them both right here, all right? QT is congruent to SR and QR is congruent to ST. Now, I already knew that QR was congruent to ST up here, but I like to write it down again, and I'm going to claim CPCTC, maybe I should say CPCTC and given, whatever, it doesn't really matter. I now know that both of these pairs of sides are congruent, so I can now say that QRST is a parallelogram, because if both pairs of opposite sides of a quadrilateral are congruent, then it is a parallelogram, right? And that was sufficient condition set 1, which is kind of cool, right? So we took the definition of a parallelogram, and we used it to prove sufficient condition number 1, right? Then we took sufficient condition number 1, and we were able to use it to prove sufficient condition number 2. Of course, the cool thing now is that now we've also got sufficient condition number 2. I.e., if we ever find ourselves in a situation again where we've got a quadrilateral that has a single pair of sides that is both parallel and congruent, we will know that that particular figure is a parallelogram with all the properties that parallelograms have. Okay, let's look at one final sufficient condition. Sufficient condition set number 3 for parallelograms. If the diagonals of a quadrilateral bisect each other, or have the same midpoint, it is a parallelogram. All right, so let's take a look at exercise number 5, where we prove sufficient condition set number 3. Given that AC and BD bisect each other, prove that ABCD is a parallelogram. Now again, just think about how kind of cool this is. If I took two segments and I just drew them so that they had the same midpoint, right? And then I connected their endpoints into a quadrilateral, that quadrilateral would have to be a parallelogram. That's what this condition set says. But how do we prove that? Well, let's mark up the one and only given we have. AC and BD bisect each other. What does that tell me? It tells me AE and CE are congruent, and it tells me that DE and EC are congruent. All right, well, that's a lot of congruent sides. Now, we also know, by the way, right, we definitely know, and this is always kind of a freebie, we know that that angle, I cannot get rid of that somehow. Okay, how about up here? There we go. That angle is congruent to that angle because they're vertical angles, and that angle is congruent to that angle because they're vertical angles. So think about this for a second. I can now prove that triangle AEB, the one on the top, is congruent to triangle CED, the one on the bottom, by side angle side. I can prove that triangle AED, the one on the left, is congruent to triangle CEB, the one on the right, also by side angle side. Now don't get me wrong, those four triangles are not congruent to each other, but the one on the top is congruent to the one on the bottom, right, because they share that angle pair, and the one on the right is congruent to the one on the left because they share that angle pair, and then those sides that are congruent. So I can prove this is congruent to that and this is congruent to that, but then by CPCTC I can say AB is congruent to CD and BC is congruent to AD, right? And now suddenly I have a quadrilateral with both pairs of opposite sides being congruent. That's sufficient condition set number 1, and therefore it must be a parallelogram. Pause the video and see if you can get all of that down into a proof. All right, let's go through it. It's amazing that we have one single given, right? Everything from that we're going to get. AC and BD bisect each other, obviously given. Let me just move this up a bit. AE is congruent to CE, DE is congruent to BE, right? And that's because a bisector divides a segment into two congruent segments. You could even probably just say the definition of a segment bisector there. I think that I would take that. I bet your math teachers would as well. Now here come our vertical angles. Angle AEB is congruent to angle CED, and angle AED is congruent to angle CEB, and that is because vertical angles are congruent. And now we can say that triangle AEB is congruent to triangle CED, that's the top triangle is congruent to the bottom triangle, and AED is congruent to CEB, that's the one on the left is congruent to the one on the right, and that's by the side angle side congruence theorem. Now we can say that AB is congruent to CD, and AD is congruent to CB, and that is our favorite, CPCTC. And finally, we can say that ABCD is a parallelogram. I wish you could just say sufficient condition set number 1, but that wouldn't get the job done. If both pairs of opposite sides of a quadrilateral are congruent, then it is a parallelogram, right? Really, really cool, right? So sufficient condition set 2 and 3 both come from that first one, and that first one simply comes from then the definition of a parallelogram. So let's wrap this up. Now, you might think, wow, that's a lot of things to sort of remember and memorize and whatnot, but they are a requirement, i.e. you're supposed to know the 3 major ways of proving that a figure is a parallelogram outside of just it meeting the definition of a parallelogram. And those 3 different conditions, right? Number 1, most important that we saw in this lesson, was that if I have a quadrilateral where both pairs of opposite sides are congruent, the same length in other words, we have a parallelogram. The other 2 are more subtle, right? One of them being if I have a quadrilateral with one pair of sides being both parallel and the same length and being congruent, then it's a parallelogram. And the final one, maybe the trickiest of them all, is that if I have a quadrilateral whose diagonals bisect each other, then it is also a parallelogram. All of these are important because you could use any one of them in the future to have to prove that a particular figure is a parallelogram. And you'll see, of course, and get much practice on this on the homework from this lesson. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.